Okie dokie. So this is going on page 88. When we are done, we're going to look at semi-log plots again, because we did look at them once before. In 2.9, we looked at them very briefly. They were just kind of mentioned, and we looked at one graph. So previously in 2.9, which was logarithmic expressions, we looked at the idea of using a logarithmically scaled axis to help us better understand data that is exponential. We now return to this idea to examine a little bit more detail through the use of semi-log plots. Okay? This is something that I can guarantee you will be on the test. It may just be one question. It may be more than one question. But if you understand the very basics of this, you should be fine no matter how it is asked. Okay? So semi-log plots, what are they? In a semi-log plot, one of the axes is logarithmically scaled. In AP Pre-Cal, we will only be scaling the y-axis. Okay? So it is possible to just have the x-axis scaled, but that's not what we're doing. We're just scaling the y-axis. That is it. Okay? And one of the big ideas that you have to know about them is that you have a semi-log plot where the y-axis is logarithmically scaled, exponential functions will appear linear. That word appear is important because they're not actually linear. They appear linear because of the way that the graph is scaled. Okay, but that's one of the things that they're going to look at to make sure that you understand, or one of the ways the questions can be asked. So when we look at this graph, this is the same graph that you had on your notes in 2.9. It's from the two graphs that displayed the population of English Americans in the current United States from 1620 to 1820. So the graph on the left here shows the population using a normal scale on the vertical axis. And we can see that for the first 100 years or so, it doesn't look like there was much change at all. Okay, and then it changes drastically as we go on. But there was quite a bit of change in the first 100 years. You just can't tell it from this graph. So that's why the graph on the right is a semi-log plot where the vertical axis has been logarithmically scaled. Okay, and we're not changing the y values. So this right here, which is at 7 million, this is 10 to the 7th, which is 7 million. Okay, it's just logarithmically scaled. It's just scaled differently. And so this says to use the features of the semi-log plot to justify why an exponential model is appropriate for the population. Now, it does not say, is an exponential model appropriate? It says justify why it is. So it's basically telling you it is, you have to tell me why. Okay? So if we were going to do a regression and we had to choose which model to use, over here, I think we would all agree we would choose exponential. Would you agree with that? Looks exponential, right? If you were going to do this one, we would probably choose linear. Does it look like a pretty decent line, right? If you're going to do a regression. And so basically that is your answer coming from this right here. Exponential functions will appear linear. So we can say, to answer our question here, I'm going to start this. Got to use my words that I have written down. Otherwise, I will probably make it a paragraph when it doesn't need to be. Yeah, okay. So the semi-log plot, oh, can't spell though. Semi-log plot above appears to be linear. And what do the little 3 dots mean? Therefore, oh, not the, we'll say and. And exponential, oh, having exponential, sorry, I'm having spelling issues today. An exponential model is appropriate. Everybody okay with that? And then I'm going to show you an example in the real world. Okay, another pretty cool thing when we get to some trick stuff. But in the real world of a logarithmically scaled graph. So y'all know what the NASDAQ is? Anybody explain to me what NASDAQ is? Stock markets, things like that. Do you know what inflation is? Okay. Do you know that it's kind of a bad thing? All right, so this is it's the inflation adjusted NASDAQ 100 index price. So this is the adjusted inflation from, I can't see what my recording thing's over here, so I don't know what that first year is, but probably in the 80s sometime. So then we got 91, 97, just in case you can't read it, all the way up to probably 2002, or I'm sorry, not 2002, 2022. But notice the Y values. They are logarithmically scaled, right? 100 times 10 times 10 times 10. Now, it doesn't have all the other little lines in it, but this is not, so some of this graphs, like if y'all are going into business, this would be definitely something that you could see in some other type of situation, not just with the NASDAQ, but if you're going to play the stock market or whatever, those kind of graphs are important to you. Just wanted to show you that like it really does get used like for real. And with the exception of these spikes, like if this spike kind of wasn't here, then would you say this looks pretty linear-ish, right? So which means inflation actually looks like that. Do you think that's good news for your future? Not really. Adulting is not good. Okay. And yeah, but anyway, that's that. We'll be depressed about that later. Okay, let's go back over here. So here's another one. Now we're gonna read through this and talk about this a couple of different ways because these questions could be asked in such a way, or your answer choices could be such that you might have to look at it differently than you do on like some multiple choice questions. They're pretty obvious because you can knock out a bunch of things really quick. But depending on what the answer choices are, it could change the difficulty. So let's look at this. So this says, after Mr. Passwater tells another one of his hilarious math jokes, it begins to spread around the school. The number of people P that have heard the joke after T minutes is graphed on the semi-log plot above, where the vertical axis the vertical axis has been logarithmically scaled. Which of the following functions could be a model for P? All right, so before we even talk about that, let's just look at this graph again, okay? So notice we start with, on the x-axis, these are evenly spaced, right? 0 to 5. Does the y-axis start at 0? No, it starts at 1, right? And we've scaled graphs differently before where, we might count by 10s or count by 20s, but everything's always evenly spaced in everything you've ever graphed, right? So now we're scaling this, and it's not evenly spaced because from 1 to 10, as I start counting these, they get closer together. And then this is 10 times 10, and then 10 cubed, right? So that's what makes it logarithmically scaled there and why it looks like it does. All right, so there's a few different ways that we could go about this. Let's look at one way that if, all this stuff kind of really confuses you, we could figure out pretty easily. What is this this point right here? What is that ordered pair? 0, 2. Do y'all agree with that? Yes? Looks like it should be 0, 1, right? But it's 0, 2 because the y-axis starts at 1. We good with that? All right, so given that, and how we know how to do equations, let's go through our answer choices now. If I substitute 0 into here, would I get 2 out as an answer? Yeah, so I'm not going to mark out A yet. If I substitute 0 into this one, would I get 2? No, what would I get? 3. So this cannot be my answer because I know it's supposed to be 0, 2, right? That's one reason why it wouldn't be my answer. On C, if I substitute 0 into here, would I get 2? What's the log of 0? Picture the log graph in your head. Or sketch a undefined. This is what your log function looks like, right? The little parent function can help you remember those things. Can you take the log of 0? No, because you have a vertical axis, right? So this is undefined, so that doesn't even make any sense, right? If I substitute 0 into here, am I going to get 2 out? Sure about that? Yeah, because 2 to the 0 power is 1. 1 times 2 is 2. So I've narrowed it down between A and B. Or A and D, I'm sorry. But I really could have narrowed it down a whole lot more because this is a logarithmically scaled graph. This appears to be linear, which means what kind of function would it represent? Exponential. And your only exponential choices are B and D, but D is really in the correct form. Okay. Now, we could have actually done this by finding the equation and whatnot, and I kind of went back and forth on whether or not I wanted to show you that, but I really don't think it's going to get that complicated. From the questions that I have seen, and you got to remember, I don't have years and years worth of stuff to look at. Don't flip it over yet. We're not done. But they haven't seemed crazy difficult. I really think if you understand the very basics of how the logarithmically scaled graphs work, you should be fine. But because of that, I want to make sure that we actually understand how to read them as well. So this next point right here, what is that ordered pair? 1, 4. So we start here, 2, 3, 4, okay? And then I'm going to ask you for one more because the other ones, like this next one, is kind of hard to count. But let's do this one right here. So this order pair, I know my x value is 4, this one. But my x value is 4. What is my y value? 30. Good. Because this is 10, 20, 30. Everybody okay with how that works? Yes? Jocelyn, you got this? Yeah? I need a nudge her. All right. So another thing. When we logarithmically scale the vertical axis for a semi-log plot, we are not changing the actual y values. Okay? Remember this here. This is 7 million. This is 10 to the 7th, which is 7 million. We have not changed anything. Does that make sense to you? We haven't changed something, but we haven't changed the actual value. All right. So to logarithmically scale the vertical axis means that the equally spaced values on the y-axis are now proportional. So I kind of already said that. Instead, we're used to having them equally spaced, but now they're proportional. Whereas the equally spaced values on the x-axis are linear, and they're equally spaced like we're used to them being equally spaced. Okay. Now again, on this question, there are lots of different ways to look through it, but we're still going to talk through every single answer here. Remember that we're not changing the actual y values, so they give us our values here. The table above gives selected values for the function of f. Which of the following graphs could represent these data in a semi-log plot where the vertical axis is logarithmically scaled? All right, so let's look at A. The first ordered pair we have is 140. Is this 140? No. Not only that, but look at the x-axis. Is the x-axis evenly spaced? No. It's logarithmically spaced, and that's not what we're looking for. We are only scaling the y-axis. Plus, this one isn't scaled, so A cannot be my answer. We good on that? All right, now when we look at B, our x-axis is equally spaced. I like that. My y-axis is logarithmically spaced. That's good. Is this point right here 140? No, it's 1 and then less than 1, right? Because this only goes to 10, so this has to be 2. I'm not less than 1. This goes to 2, so it's 1.8 or something. It doesn't even matter because it's just not it. Okay, we good with that? All right, so let's look at C. Is this point 140? Is this 260? Yes. Is this 390? Yes. Is this 135? Yes. Is this 203? Yes. Okay, so let's look at D. Is this 140? Is that 140? Yes. 260? 390? 135? 203? Yes? Okay, so this is evenly spaced. This is evenly spaced. Is this logarithmically scaled? Yes. Is this? No, it's equally spaced also. My answer is D. Now, a few of the questions that I have seen are basically this simple. And if it, from the very beginning, it said, I mean, it flat out tells you vertical axis is logarithmically scaled. Well, that could, if you look at that first, that could automatically eliminate A and C. B is logarithmically scaled, and this is evenly spaced. So both of these are logarithmically scaled, but then when you look at your actual data, it only fits in this one, okay? And I think you'll recognize the semi-log plot because they look weird, right? I mean, and you kind of know what they look like, you'll be okay. All right, grab your other sheet of paper. It's also going on page 88. I don't know what happened to the title on this one, but... All right, so we're going to plot points here. Plot the following points on the same coordinate plane. So I'm going to plot 0, 200, and I'm right there. Okay. And then I'm going to give you a minute, and I want you to plot the other 4. So once you're done, check yourself with me. If my points are off a tiny bit, it's hard for me to hit where I'm actually aiming sometimes. So try to get in the general area. Plus the ones with the decimals, you're kind of just estimating anyway. That just shows that, you know, make sure that you understand how it counts because it is very different than anything that you are used to doing. Okay. Are we good with all that? Beautiful. All right. So then, as we've seen, if we graph an exponential function on a semi-log plot, the graph will appear linear. Okay, because remember, it's not. It appears linear. That's fine and great. In this case, we can create a linear model for the graph. Okay, so our linear model for a semi-log plot, given the exponential model in this form, y equals a times b to the x. Don't have a ton of other transformations going on here. We're not going to get crazy difficult with this. The corresponding linear model for this semi-log plot is given by this. This is just an equation for a line. This is y equals, this is your slope times x plus the y-intercept. It's basically y equals mx plus b. However, the b in the linear equation and this b are not the same b, right? So the way I'll write this out then is that y equals mx plus your y-intercept. Because I don't want to use b and confuse things. But that's what y equals mx plus b is, right? Slope, intercept form. And so we know how to find slope. We know how to write equations of lines. It's not that big of a deal. So then it says here, the slope of our linear function is log base n of b, which is this part right here. And the y-intercept is log base n of a, which is right there, which is basically what I just said. Now, the n, the base n corresponds to the base used for the scaling of the vertical axis. Again, I don't have millions of questions to look at, but I have not yet seen one where it wasn't base 10. So, and I have a feeling, again, they're going to keep it kind of simple and basic. So I think base 10 is probably, but that doesn't mean it couldn't be a different base. So just know that. But we'll be able to use base 10 here. So we are going to write the equation of a line. It's going to look really horrific because it's going to have the word log in it a whole bunch. It just makes it look worse, okay? But it's not going to be any more difficult than anything you've done. I just want you to remind yourself of that, right? Sometimes we do stuff and it looks insane, but it's not that bad. So the first thing we're going to do is we're going to find the slope. Well, in order to find the slope, I need 2 points, right? So this point, well, I don't have one at 0, but this point right here, this would be 1, what? Put that down, you're driving me nuts. 1 what? 40, good. And this next one would be 260. Okay, we agree with that? Now remember, the y-axis is logarithmically scaled. So when we so to find the slope, it's just the change in y over the change in x, yes? So my y values, which are 60 and 40, but since this is logarithmically scaled, I need the log of 60 minus the log of 40. So you got to stick a log on all of those. So log of 60 minus the log of 40 over 2 minus 1. Okay, so it's still slope. It looks like it's way more difficult because of that, but it's no big deal, right? So I know that 2 minus 1 is 1. So this is just the log of 60 minus the log of 40. Does that become the log of 20? No, it does not. Can I condense that? Yes. That would be the log of 60 over 40, right? And what does that reduce to? Log of 3 over 2. That is your slope. Have you ever had a slope before that had a log in it? No. Is it that big of a deal? No. Okay? Because remember, this just represents some number, right? You don't know what the value is, it doesn't matter at this point. We all good with that? Okay. So I have my slope. I also need my y-intercept if I want to put it in that form. So I'm going to come over here and I'm going to write out what we have so far. We have y equals the slope, which is log of 3/2 times x plus, and then the y-intercept is going to be the log of a. And notice if I did put a b there, the b is over here for my exponential, but it's just the log of a, whatever it is. And I want to figure out what the log of a is, yes, to get my intercept. Now, so I can do one of the ways that you did this anytime you did y equals mx plus b. I have my slope. I have a point. If I substitute in a point here, my only unknown will be this, and I can figure that out. You with me? We can pick any point we want. I say we go with the easy one that has a 1 in it. Okay? We're going to use that point. Now remember, our y-axis is logarithmically scaled. So when I put in that 40, this is actually going to become the log of 40. It's going to equal the log of 3/2 times x plus the log of a. Oh, I put x. Oh my gosh. No. Wouldn't it be a miracle if I could get through a day without doing something stupid? What is my x value? 1. So it's really just times 1, but I'm going to put that in there just so that, because maybe sometimes you don't get to use 1. Maybe it has to be something else, but 1 makes it the easiest for sure, which means it doesn't really change what that is. Now I'm trying to get log of a by itself, so I'm going to subtract that log that's on the right over to the left. So I'm going to have the log of 40 minus the log of 3/2, and that's equal to the log of a. All right, well, can I condense what's on the left? Yes. So this would be the log of 40. Now, it's 40 divided by 3/2, right? But I don't want to make it look insane. So instead, I can say 40 times what? 2/3. Okay? Not 3, but okay. Equals the log of a. So that means that this is the log of 80 over 3 equals the log of a. Any questions at this point? Here's the other thing. They remind you multiple times, which is a very good thing, what the form is and like what all your variables are, so you can kind of keep everything straight. So what we have here is this. Y equals, because it says write an equation for the linear model in a semi-plot form right there. So it's y equals the slope, which we found right there, log of 3/2 times x, plus the log of a, which we found right here, that's the log of 80/3. Yes. What I do? Because I'm dividing. The reciprocal, yeah, that's a good question. I'm sure you weren't the only one thinking. Everybody else, we're good on why that 3/2 became 2/3? Yes? Okay. All right. Is everybody good with where all this came from? Does it look weird? Yes. Does it look like it's way more difficult than other stuff? Yes. But if you look at what we did, it's just got a bunch of the word log in it, and we had to use a log property. No biggie. So now here, it says from the linear model in part A, that's that right there, write the equation of the exponential model in this form. Well, in case you get things mixed up, look at what this tells me. This is the log of B. This is the B, and this is log of A, right? So when I want to put it in that form right there, that means it is y equals, what's A? 80/3 times B, which is 3/2 to the x power. Now, right here, can I cancel out those 3's and divide by 2 and get 40 to the x power? No, not unless you want to be wrong and look ridiculous, right? Okay. What questions you got? So make sure you have all those steps written down, because when you get to one of these, I know what I'm going to hear from some people. This is so confusing, it's so difficult, and I don't understand it. You know how to do lines. It's just got the log stuff in there. And again, they repeat over and over what the pieces are. You can do that. You can put those pieces together. I know you can. All right. What questions you got? We good? All right.